Into this computer. Hello, this is Battery Knowledge Transfer episode 4. Hello, testing. Okay, cool. Share screen, slideshow. I'll hide this. Okay. Hello, everybody on Zoom and everybody in the classroom. So yes, obviously we'll be continuing the slide deck that I have made at this point like a month ago. So yeah, obviously let's talk about battery cells. A big thing that was obviously discussed, but Dennis will probably affect you most significantly is actually battery cell selection, how that affects the overall pack configuration. A big part of the mechanical element of the battery pack is how we package all this together, but obviously a lot of the rules and limitations about the actual segments and the pack configuration come on the electrical side, not the mechanical side. So while you have to be working with the mechanical side to do with the actual physical packaging, force distribution, heat generation, all that, you have to constantly be looking at our rules compliance to make sure we're storing as much energy as possible and we have the highest power output possible, or highest power output that sort of meets our requirements. So obviously thinking about cells from the most fundamental level, when you're picking cells, you want to make sure your whole pack should have cells selected and configured in such a way where it lets you finish endurance. When we came into this year, we didn't have a good model that told us how much energy we were going to consume during the race. And so we looked at other teams and said, okay, cool, other teams use 5 to 6 kilowatt hour battery packs. And so since our battery pack is like 8 kilowatt hours, we said, oh, okay, we will have more than enough energy to finish the race. And that was how we originally spec'd that. And the reasoning is because if we wanted the 80 kilowatts of power output, that was the big limiting factor of why we picked 4 cells in parallel, is because if you go to 600 volts and then you have the 180 amps going out of our pack because of the 45 amps per cell, and then you do your heat loss calculations, you figure out that we can get out about 70 to 80 kilowatts of actual work from our pack as a reason. So it comes from a power requirement number, and we said, oh, we have more than enough energy. Obviously now with our more updated models that were produced during this year, we've now figured out that we probably are going to have not enough energy to finish the race, and we will be generating a lot of heat as we really push our car. This is yet to be seen with obviously the actual empirical testing that we do during before and then during and after comp. But yeah, obviously one of the big things as well is not only do you need to store enough energy and output enough power, you also want to generate as little heat as possible. This is a pretty logical one. The more heat that you generate, the more energy that you're wasting, specifically at higher power outputs. And obviously then you have to have bigger cooling solutions that are heavier and more complicated design with more failure modes. So if you could have an ideal cell that had basically zero internal resistance, that would always be preferred. And that's actually one of the things about something like a pouch cell is that pouch cells, oftentimes you can find they'll go down to, ours currently are 16 milliohms of internal resistance. You can get pouch cells down to a half a milliohm. So you can get them way lower. The problem is that obviously it's significantly harder for us to source pouch cells, and then there are other complexities that come from them because the fact that they are not a rigid body. Yeah.
Pouch cells with low resistance is also often higher.
I don't know. That's something that I know that we've seen some trends from our preliminary research, but that's something that whenever people want to make that leap over to pouch cells, whether that is in 2 weeks or in 5 years, I don't know, or maybe never. I think pouch cells is something that someone at some point should do a lot of research into and really mature the idea to say, okay, cool. If we were to pick pouch cells, here would be our 2 or 3 different options, and here are the actual benefits that we would see and the concerns we'd see. Because right now we have some high level ideas and some reasons I think it might be cool, but actually getting a really good understanding of, okay, what exactly is the improvement we see? What exactly are the benefits and drawbacks? But be great. From what I can tell, in the US, they seem to have gone out of style. I found images of teams in the US, like MIT, that ran them back in 2014, 2016. But then from what I can find, all the teams in the US now appear to run cylindrical cells for reasons that are beyond what I understand. From my understanding, Formula Student Germany and Formula Student over in Europe, a lot of teams do use pouch cells. But they also and there are 2 or 3 pouch cells that are super common over there, just like the P42A that we use, pretty common here. But that's something that, to my knowledge, they also have a different rule set than we do. So it may be that they have increased access to it, B, reduced tariffs, or C, maybe their rule set enables it in a way that ours don't. We don't know. But I do know specifically like the cell level fusing and cell level bonding requirement that we have. To my knowledge, that may or may not exist in the Formula student rules, because I talked to one of their battery designers. So you know how we need to have these bonds that go to every every cell, like that. The whole reason we talk to Hess is so we can do the cell level bonding. And so that means you then have overcurrent protection for every battery cell. When I talked to the European teams, they were like, "What is that?" And so maybe it just happened to be that the people I was talking to were unaware, weren't involved in that part of the battery design. But I haven't looked at the Formula student rules, but maybe they also don't have a bonding rule. I don't know. So I don't know the answer to that. From what I have seen of pouch cells, I don't understand how you connect them properly, because a lot of the pouch cells that I have seen just have tabs. And tabs, normally you would solder a tab or you would bolt a tab. And the problem is that if they have boltable tabs that come out the end, then that's awesome. You could just bolt it, which would be great. But if they don't have boltable tabs and it's like a solder tab, then I have no idea how you would do that, because you can't solder in the high current path. That's just like a rule. So I guess maybe you could clamp it. I don't know. And but one thing that we have seen is when we look at really, really high current output individual cells like Pt.4s, even here in the US, some of them will just have bolted ring terminals like on the end of the cell itself. And since that exists, I wouldn't be surprised if when you go and find an actual like perfect, like the pouch cell that all the student teams use in Germany, I wouldn't be surprised if, you figure out that, it actually has like a really nice, easy boltable connection. I don't know. Yep. Yeah, cool. And then obviously a thing that it's pretty straightforward is just having as much energy density as possible. So that's things that right now, when I say energy density, I mean two things. I mean both energy per unit volume and energy per weight. And those are two separate but also very important metrics to go by. Generally, you will find that those go hand in hand, that if you have something like a lot of your cylindrical cells in one size class will all weigh basically the same. And so something that has higher energy density per pound will also be higher energy density per liter. But as you move into pouch cells, that's definitely a comparison to be making, is not just, does this have more energy density per pound, but also is it actually more energy density per unit volume and all that. And then obviously all that comes into the larger consideration of how do you cool it. Like if you figure out that pouch cells actually don't need any cooling, then even if they are less dense, let's say, the reduced space consumption by having reduced cooling could already make up for that. So yep, that's like a whole new thing to look into in design. Obviously, like I said, our current battery cells is the model cell P42A. It's just like if you go onto a battery selling website, you'll find that that is just like the common one. There are lots and lots and lots of battery cells, but if you basically look and say, I want really high power output and I want really high energy density, this is like a standard option. And that's why, at least from my understanding, that's why this is used by big automotive companies. And that's why this was the battery cell that was sponsored by Tesla. We picked it before we knew that. But it shows that we picked pretty well if the 21700 battery cell that Tesla offers is this exact one. I should note that we obviously picked this going on 2 years ago at this point. So obviously battery technology has matured a little bit since then. I believe Joshua came across that they actually have a slightly revised version of this design that has a slightly higher energy density now, the P45A, B, something, B, the P45B. And so maybe that's something to consider, is if you want a little bit more energy density, but you don't want to really change anything big about the design, maybe that would be something to look into, is moving to a slightly higher energy capacity battery cell. Yeah, and see, there you go. And so with obviously you see improvements in battery technology every year, so it might be worth just constantly not just copy pasting the same cells over and over, but really redoing that analysis every year to say, hey, has anything new come to market that can really change? But then obviously with that comes additional complexity. Like right now, we're obviously in the 5 point something megajoules per segment, and there's the rules limit of 6 megajoules per segment. So, hello. So if you were to step up to using something like the P45B instead of the P42A, you now have an extra 300 milliamp hours worth of energy in your batteries. And when you add all that up, that may end up running you over your energy capacity per segment. I don't know. And so that's important to check that. Cool. And then yeah, obviously I can run through the specs, but it's like you can see what they are on the screen. So yeah. Okay, so yeah, the current actual design. Obviously, I have a little calculator in here that's linked that can do a whole bunch of stuff that tells you the electrical properties of the battery pack. One of the nice things that I included in this calculator is it can just. I'm a big fan of making Google Sheets that automatically calculate things for you. If you need to do something once, do it once. If you need to do something more than once, or you ever need to like test and iterate and refine and improve, Chloe has experienced my harassment about this many times. That if you need to ever iterate on something, use a Google Sheet to do the math for you, do the math out by hand once, and then do the rest of it in a Google Sheet. And the idea is that this sheet lets you, if you say, oh, I want to move to a different battery cell, you can plug in the new specs of the battery cell, and it'll automatically pump out the new battery characteristics for you. Actually, let me see if I can pop it up. So yeah. Yeah, so like for example, in here I have all the characteristics of our battery cells where you have the peak, nominal, and under voltage of the cells, the maximum current, and nominal current, energy, internal resistance, all that. But then now suddenly, let's say we move to the new ones where instead of having that, let's say it's like 17 watt hours and we've moved down to like 10 milliohms resistance, you can now see it automatically updates both our pack resistance as well as the energy capacity of the pack now jumps up. And so it's pretty nice to just put together sheets that do these things for you automatically rather than having to redo the math every time. Because the rule of thumb that I always go by is if I have to do math more than twice, I probably should automate it. Because by the time you get to like the fifth time, you'll be like, why am I doing this math by hand every time? So yeah. But yeah, so this sheet exists and it'll automatically calculate everything for you. You can feel free to make your own too. This is just in the drive. Just zoom back in. Cool. And then the big thing is looking at our current battery design. Obviously, our current design as a 140S4P configuration. As a reminder, that means 140 battery cells in series, 4 in parallel. So what that tells us is that we obviously have the 4.2 volts peak per cell adds all the way up to our 588 volt maximum. And then the maximum of 48 amps per cell output with the 4 in parallel gives us 180 amps output. What's up? Yes, continuous rating. Peak ratings are even higher than that. So that is sort of the configuration that we landed on. One thing that I would like the big thing that I want to voice when we did this configuration is we kind of just said, yeah, we want to get a maximum voltage that is as high as possible. Because we went for the pretty trivial idea of if you can output, 180 amps, 600 volts, or 360 amps at 300 volts, you're always going to have better efficiency by going to higher voltages. Like that's why, power lines and everything go at monstrously high voltages and use AC. It's because it generates less. So that's why we went to go as high as possible. But obviously, we've already talked about all sorts of different techniques of, you can maybe limit the voltage on your cells to be able to get your nominal voltage higher, even if it means you're wasting a little bit of energy. Or same thing. This one was targeting to be able to output like 80 kilowatts of power basically all the time or as much time as possible. But maybe that's not the correct solution. As we've already found, our car can do, for like the amount of torque that we can output for most of the speed of our car is unnecessary anyway. So maybe we would actually have a more efficient car if instead of having 80 kilowatt output all the time, maybe we just say, oh, let's do 65 kilowatts. Because maybe if you run the simulations and you do all the modeling of the car, you might actually find that that's faster. I don't know. So definitely there's a potential that our battery is overkill in that regard. Like I already talked about, total energy capacity at 8.7. That's a lot more than most other teams. Don't know why. And that's something that I think is the really big thing I want to emphasize, is that's why I think regardless of what happens with Count this year, regardless of anything, this car needs to be driven through a full endurance somewhere, somehow. It doesn't matter if it's here. It doesn't matter if it's in Michigan. It doesn't matter if it's over the summer. It doesn't matter if it's in fall. This car needs to be driven before we can really pick and finalize a new battery design. Because fundamentally, we do not know if any of our simulations are even remotely accurate. Obviously, Ben has simulation tools that are great, and they try their best to give us an approximation of how much power we're going to use, but that's fundamentally just a simulation tool. And so we really need to actually drive this car and get it out there. Because until we do that, you can't really meaningfully iterate on it because, maybe we get out there and it turns out 8.7 kilowatt hours is way more than we need. And we don't have to worry about more energy. Or maybe his simulations are right and maybe we do need more energy. That's something we cannot know until we actually go to it. I already talked about the peak voltage and peak current and continuous current. Those are all just to get us to that 80 kilowatt number. And those are the specs that fall out of the way you divide stuff through. Obviously, the reason it's 588 and not exactly 600 is because we went into it with the approach of we didn't even think of the idea of doing like a voltage limit on each cell that wasn't the default. And so when you divide 600 by 4.2, I think you get like 142 point something. But then 142 point something, obviously you'd have to round that down to 142, and that doesn't divide evenly by the 7 segments that we have. You could obviously make your segments different, but then you need to have a BMS that supports different amounts of cells per segment. And then firmware that supports that around that. So it's totally doable, but we were like, yeah, let's do the same configuration every segment just to make it easy. But that's totally allowed by rules. You can totally have different segments with different, like as long as all of them can handle the current flowing through them, as long as they're rules compliant, you can make your segments be different, weird. Every team that I've seen has run the same configuration in every segment, but there's also the teams are improving and changing every year, so maybe we could be an innovator in that. So
I realize I've never asked this, but why do we have 6 8x10s and a 1 4x1?
yeah, the physical geometry of the car. Yep, we basically what we did was when we were first designing the actual battery pack, and this will get a little bit into the actual pack configuration stuff that we'll talk about at the end of the slide deck. Is we asked the chassis lead at the time. We said, "Hey, can you give us basically like a block model of what is the biggest space that we can fill up for the battery?" And so he gave us that block model and said, "Okay, cool. Here is the space you can fill up." We now, in hindsight, realize that that was not the correct approach because number one, the frame can be changed and shifted and stretched to match requirements. And then number two, he didn't really account for the fact that the frame was going to change a lot to house a battery. And so there was a lot of space that was wasted and not effectively utilized, especially underneath the firewall and near the differential. And then we stretched the battery in the wrong directions by stretching it upwards and even backwards. And so that meant that the motor is now super tight with the actual battery, which is bad. So it meant that a lot of stuff got really tight because we were sort of misguided, and that was a failing on both sides of the chassis lead at the time, not really thinking about the context and basically just giving us a block model of the motor at the time, of the engine at the time. That was essentially all he did, was just a block model of the engine. And so that meant that we fit something in the shape of the engine, but then once you added all the walls and layers outside of that, it caused problems. But yeah, that's why we do 6+1, is because we literally hopped into like VR CAD and drew a bunch of different shapes and then played around moving them around in space to see which seemed to fit most effectively. And the answer for us seemed to be 6+1. And the one is just try to fit under the firewall. My recommendation for upcoming years is to do that more effectively. Try to use, because the space right now under the firewall is very much underutilized, and we have a very tall battery. It would be much more optimal to reconfigure the pack in such a way to move as much weight as possible under the firewall, because then that's moving it closer to your center of gravity. So that's lowering the moment of inertia of the car, lowering the center of gravity of the car, and making the battery and taking more cells away from areas that have a bunch of other shit that needs to be there, like the inverter, the motor, the differential. So, whole bunch of reasons why we want to change it. Hindsight is 2020. So, make sense? Cool. Yeah, just to run off a few other numbers, we already talked about the pack has about a half an ohm of resistance. So that means whenever you're drawing current from the pack, you can calculate how much heat is being generated by it by just looking at the current squared times that resistance. And that gives you a pretty accurate number. What this translates to at our maximum power output is up when you get up to that 175, 180 amp power output number, really all the way up there at the top end, you're generating something like 17 kilowatts of heat. To put that in perspective, that's like a little more than like 10x the amount of power you can get out of a normal wall outlet, because most wall outlets are in the range of like 1500 to like 2200 watts, depending on the rating. So we're talking that's just heat. That's not actual power that's doing work. That's just heat being generated to heat up the battery cells. So fun time. Same thing, our battery, just cells alone weigh basically 40 kilograms. So you're talking about like 100 pounds of just like battery, a little bit less, it's like 90 something. You're talking basically 100 pounds of just battery cells. So those are pretty thick, and that's not something we can really change. Like with the amount of battery that we want, we're already pretty high energy density. And so if you wanted to lower that number and make the battery lower weight, then you would have to move to less cells. Yes, so that's the thing, is that your heat generation is strictly a function of your resistance and then the current you're drawing from the pack. And then obviously there's a bunch of equivalent alternatives to that, but yeah. And the reason that we're looking into the better cooling methods is because yeah, there are cooling methods that can actually keep up with this 17 kilowatts of heat. But yeah, because right now I think our air cooling numbers put us in the range of like 2 to 3 kilowatts of cooling, which is not great. What's up? Yeah, the TLDR for pouch cells is, our preliminary analysis says that they have a much lower internal resistance. And so what that tells us is that we may be able to get away with just like putting essentially cold plates next to the pouch cells and not worrying about it. Because if our like because I think the best pouch cells that we found had like a 30th, so like 2%, 3% of the resistance. Because think about it, if you're going from 16 milliohms to a half a milliohm, that's basically 1 over 32. And so you're talking like 3% of the resistance of our current batteries. It's like, actually, because we can hop into the calculator and you can see exactly what happens. Let's say we use the exact same energy density battery, but now suddenly it has an internal resistance of only half a milliohm. You can say the resistance of the whole pack drops to 17 milliohms, and the peak heat generation is 2.3 kilowatts. Well, that was when you Google pouch cell internal resistance, you find that it says they can go as low as 0.5 milliohms. But like that doesn't, we have not put in the research or effort to figure out like, oh, is there actually, yeah, like that could also be a cell where it's like, oh, maybe it can do that, but maybe it doesn't have high energy density. Or maybe if it does have high energy density, maybe it doesn't have a high current output. Or maybe it does have all of those things, and maybe we just need to find a vendor.
So brief Googling first result for 4.2 amp hour pouch cell is less than 120. Jesus. Wait.
120 milliohms is massive.
Yeah.
Yeah, and so that's the thing, is that it's like, well, when you go and you find find a generic pouch cell, you're like, oh, well, that one has a massive internal resistance, and so maybe we're seeing two ends of the spectrum. If you want high capacity, maybe you don't get it, and so maybe the trade-offs actually aren't as beneficial, like because it's really easy to look at a space and say like, oh, this has all these benefits, but it turns out none of that. So, and so that's why I'm saying like pouch cells may be a great benefit, but they may also not be. And like I said, obviously there are other complexities that come with them because of the fact that they are just bags of soup. So maybe don't stab these. But yeah, same thing. The big thing also when it comes to volume, I don't have a good way of visualizing volume. Like maybe you have a good one, but like if you tell me something is 15 liters, or like if you told me something's a foot by a foot by a foot, I'm like, cool. But if you tell me something is 4.1 cubic feet of volume, like that doesn't translate well to me intuitively. So if you can find a good way to think about cell volume, that's great. That can give you a really quick, rough estimate of how big your pack is going to be, when you account for the fact that you have like cell packing inefficiency and all that. Cool. That's the thing, is like if you have a good unit for, if that's a good way for you to visualize it, then that's awesome. And so that's the big question. 4 Borgs. Oh boy. And anyway, But yeah, and so then these last two numbers, both the 17 kilowatts of heat and the 80 kilowatt power output. So yep. But let's see, is it still catching my? Yes, it's still catching my voice. Okay. So yeah, obviously we talked, to the end of the earth about pouch cells already. It would be a massive design shift. Like your cell holder completely changes how you're doing bonding is completely changing. Probably it's a completely new technology. You have new issues and concerns, new cooling methods. Everything is completely different. It would definitely be less work than like completely restarting from the ground up. But now and I still think in hindsight, cylindrical cells were the safer of the two options for us right now. But I do definitely think that like pouch cells are something to give a serious look to at some point in the future, given the fact that all three of you are going to have at least another year or two here on the team, if not more. I think you all have time to cook on it. I think it would be cool for someone and something to actually do an investigation because you're sophomore, freshman. Cool. Okay, so then yeah, all of you have plenty of time to cook on this team.
You're a freshman?
Yeah, and so it might be that maybe by the time y'all are actually like done here, you may actually move the team to pouch cells, or maybe not. I don't know. Or cost could also be a big consideration. Not sure. I've already talked about this. My TLDR for this upcoming year is since we already have a new shipment of cells from Tesla, it's probably safe to just like use the same battery cells. For the following year, it might be good to actually start seriously looking at moving. Or alternatively, if you can find the list of cells that Tesla sponsors, they do get their sponsorship stuff arrives in like November. And so what you could do is you could also figure out what were the 4 or 6 battery cells that they did. And you could maybe design with that in mind. Because they basically everyone who applies wins.
So the shipment from Tesla, that's from this past November?
Yes.
Okay. Is that is that separate than what we're using right now for the current cells or?
Yeah, so we bought 600 battery cells. So that was 560 for the pack and an additional like 40 something for testing and miscellaneous use. For like this car. And then we basically, I don't want to say lied. Lied is a strong word. We presented a new hypothetical battery design to Tesla and said, hey, we want battery cells for this. And they sent us an additional 560 cells. So there are currently like 1,200 battery cells in the office, 600 of which are, 500 of which or so are in the current battery. And then another 500 or 600 of which are just in storage boxes waiting to be put into the next battery. Like I said, so that means that you don't have to worry about sourcing cells for next year. But like I said, if you do the investigation, you find that, we really like gotta move to a pouch cell, then it may be worth putting the effort to look at the cells that Tesla offers. And going and potentially and like fleshing out, I don't know if it means moving to it, but fleshing out a design with that information in mind. So cool. And then obviously, yeah, a few other things that I already mentioned earlier in the presentation, but I'll sort of flesh out a little bit more here, is the idea of lowering the maximum voltage per cell to get the nominal voltage of the battery pack up. The reason that you would do this is, let's say you care less about energy density and more about power output. Right now with our pack, we start at 588 volts, but then within the first little bit, we pretty quickly drop down to about 500 volts. And if you do the math out, 500 volts at 175 amps, which is what our fuse is, like 500 volts, 180 amps, and then you do all the heat calculations, you figure you're only actually getting about 70 to 75 kilowatts of power out of our battery. And so that's one of the unfortunate things is that our battery, even though it can output like 90 kilowatts of work, it actually most of the time only does like 70 because our nominal voltage is so much lower. And so that would be an advantage is that even if you don't need the extra energy capacity, but you do want the car to be able to output 80 kilowatts for longer, maybe what you could do is you could say, all right, let's limit it to 4 volts per cell. And that now means that your nominal voltage would, because I think I even did this math out. You can do it in the calculator that I had pulled up. If you drop your peak voltage to like 4 or 4.1 volts per cell, you can now get the pack like with 150S, your nominal voltage can now go up to like 550. And 550 means that now you can output 80 kilowatts until you're at like 30% state of charge with the same cells. So that might be an advantage. Maybe you can use the same cells and then be negative. But that obviously means that the resistance is also going to go up a little bit more because you now have even more cells. So, yeah.
With the off-off is what I found is 17 amp per hour, 3
volt, pouch pack cell with 3 million ohms.
There you go. And so that's the thing is like if there's a button. Oof. 17, so that's 4 bars. Yeah.
And our 4P is 4 million.
Oh, well, so each one like 5.5, so it's about the same.
Yeah. And so so that one happens to be roughly equivalent, it seems, where it's about the same resistance and about the same capacity.
Yes, I think part of the reason. I think part of the reason that we were seeing a lot of pouch cells with much lower internal resistance. You can get like a massive pouch cell with a low internal.
Yeah, and so maybe that's the thing is maybe we were just maybe the numbers we were getting quoted were monstrously parallelized cells.
Not even monstrously parallelized. You can just get a bigger cell.
Yeah,
a single bigger cell.
Oh, I mean internally, yes.
It is not.
Is it
a bigger sheet of chemicals?
But yeah, and so that's the thing is that it's like maybe it turns out that pouch cells are not the saving grace that we hoped. So don't know, and that's what I mean is like going through and actually maturing the design because clearly someone somewhere thinks it's a good idea. So
You asked them what pouch cells
they told me a name, I don't remember what it was. Because of the fact that I'll be going back to Tesla, I may actually be able to tell you because I will re-see a lot of these people, so I may be able to tell you what those answers were. Yeah. So I might be able to get that information for you guys, but I'm sure you also could just reach out to them, or I'm sure someone on the Reddit has publicized the cell that everyone uses. So I definitely do recommend when you're looking for weird stuff like this, when you're trying to find like, oh, what cell did Tesla have, or what cell do a lot of teams in Europe use? Like that was how we figured out that the MRAX motors are so common. Is just like go on the Reddit and then like look around, and until you're in the space, the Reddit is like the best way to figure out. Okay, what are norms? And then once you go to competition, you talk to everyone. You go, oh, okay, I see. Everyone uses the same shit. Cool, good to hear. So yeah, cool things to think about. Yeah, I already talked about all this. Cool. And then one of the big comments that I mentioned in here is that obviously right now we use a 140S 4P configuration, but you could obviously move down to 3 parallel or move up to 5 parallel with additional benefits and costs. So obviously if you move down to 3 parallel, your size and your energy capacity is now going to go down. So let's say the car, you still want to run at 600 volts, but maybe you only want it to be a 60 kilowatt car instead of an 80 kilowatt car. And you didn't need as much energy or whatever, then maybe moving down to 3P would be beneficial because then your pack can be way lighter and way smaller. Obviously, that means your resistance is now going to go up, but if you're drawing less power, maybe that's fine. Alternatively, let's say you guys look and you say, oh yeah, we actually do burn this much power and we do really need more energy. Then another alternative option is you could maybe bump up to 5 parallel, where if you do 5 parallel, now your resistance obviously has gone down, which is great. So that means your pack's going to generate less heat and can output more power. And so that's how Teslas work. That my Tesla has, like 100 in series and then like fucking 12 in parallel, or like 15 in parallel, or 20 in parallel or something. And so that's why they still generate a lot of heat, but they don't generate nearly as much. Because like if you want to draw 100 kilowatts from my car versus 100 kilowatts from our car, my car has fucking 10 times as many cells in parallel. And so the resistance of the pack is like a tenth of what ours is. And so you're generating a tenth of the heat. So my car for the same output might do 2 kilowatts of heat instead of 17. What's up?
So,
Nope. If you only cares how many series. Well, it cares how many series in a segment. Yep.
What's the power up for your cell?
Let's Google it. I think it's like, 387 kilowatts. Yeah, so there you go. So it's like, got some sauce.
Wait, does Tesla use like pouch cells or like cell cells?
like normal cylindrical cells. If you have an older car, they actually are using the P42As or similar. Yeah, now if you have one of the newer cars, anything coming from the Texas factory, any of the newer Model Ys, they're gonna have the 4680 cells, which are their newer ones that they have that have way higher energy density, but they also lose so much space in between the cells that they get bigger. Because like as your spheres get larger, the gaps between them get larger. So they actually end up having like similar or lower range to the previous one, even though they have higher density per cell. But yeah, so this is the big thing about parallel is that it's like I do recommend strongly that like especially like Dennis, this is going to be a big lift on your end, more than anything else on the mechanical end, is looking in and saying, okay, cool. Looking through all of these different options of okay, cool, what if we change the series count, we drop the peak voltages, what if we change the parallel count? Working with the mechanical teams to figure out how that affects packaging and segment design and configuration, all that. I do think that's a great place for you to start because that's fundamentally way more math in your domain. And then once I think the optimal solution would be to come to 2 or 3 different options and say, hey, here are the best ones that I found that really effectively solve our problem. And then working with mechanical teams to say, hey, how do we now implement this mechanically? Because you can do preliminary packaging on your own, but you definitely want to be working with mechanical teams to say, hey, how do we actually package this into segments? How do we distribute this weight? How do we do the actual segment configuration in the car?
I want to like ask, like, what does a well-integrated battery look like?
Yes, exactly. Good question.
Yeah.
I don't know the answer.
No, not you. Like, just like that's like a I think that'd be a big back and
Yes.
forth. Just like okay, so like like I'm talking with like Ben and just other mechanical people saying like,
Stick. That'd be cool.
Yeah.
Is he gonna be? Is he box or is he accumulator? Cool.
Whoever Ben.
All right. Awesome. But yeah, so that's the big thing is it's like that's why a lot of people ask me, they're like, oh, they keep like a lot of people on the mechanical side keep coming to me and being like, what do the electrical people actually do in the battery? It sounds like it's all mechanical stuff. I'm like, because all the stuff you've seen this year has been mechanical, because all the electrical work was already done for it last year. And we've now learned in that process that there's so much more electrical work to be done that we just didn't do because we didn't know. So yep. A lot of great options, and I look forward to you figuring it out because you're gonna have to figure that out like before the frame is designed, which will be over the summer. So good luck. Yeah. All right. So I'll kind of skim over this part because this part isn't as important. But the actual cell configuration stuff, the segment configuration is a little more important, but the cell configuration has impacts on the segment configuration. So the part is like initial design, blah, 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 all that stuff. Let's see. I obviously don't remember these slides as well, so let me skim over them real quick. Yes, okay. So the big parts that I want to emphasize is it's important both how all the segments are oriented relative to each other, as well as how the cells are packaged within a segment. The reason I say that is because let's say you have a super efficient packaging of cells within a segment. If you now don't have an easy way to connect those segments together, then even though you have a really efficient segment, then your whole pack is actually very inefficient. And that's actually what we ended up doing is that we tried to make a very efficient segment and then made a pack that wastes a lot of exterior space with maintenance plugs that don't make any sense. And like wiring space that doesn't really work out and for load paths that don't really work. And so that's why you want to make sure you're doing these two sort of back and forth. Because yeah, basically all of your initial design effort should be looking at alternative designs for segment internals and then multiple segment configurations. Because once you land on a really good one, then you should have since we already know all the stuff that goes into a battery, and that's what we covered in this presentation, you should know what are all the things you have to consider. Like, okay, where does the BMS go? Where does the wiring go? How tall or like how do we do the wiring for sensing? How do you do all the bonding heights? How is everything bolted down or how are things adhesed, whatever? And so all those things. And once you figure all those ideas out, you can then get a block model ready. And so while the battery pack design gets matured and finalized, refined, that can be handed over to like the actual frame team and the box team to actually start building and designing a box for it and designing a frame that goes around that. So yeah. Yeah, okay. So first I want to talk about cell packing. I know I've mentioned this previously in the designs, but the big thing is that there's two main ways that you can pack spheres. Because you can think about a cylinder as fundamentally just like an extrusion of a 2D circle. The way that you're probably most like familiar with, the way that you've probably seen the most often is square packing, where you basically pack things on a like an up-down Cartesian grid. It's not as efficient. I think it only has like 76% packing efficiency. Um, because if you think about it, it's pi over 4 is the like efficiency rating of that. And so you have a lot of ways to do it. But if you have something to put in that space, then maybe that would be more optimal. One of the things that was discussed was, let's say you did a cold plate on one side of the battery pack. You could have like heat transferring tubes that could run up in the middle in these areas, and that would now give you more space. Or let's say you wanted to bolt your battery pack together. If you need to run both through the battery pack, you then have space in there to run a bolt through your pack. So that configuration, even though it may be less dense, it may have more flexibility and more options. What's up? Apparently that's common.
So like, how do you see that bolt through without like access to
I think the idea is that everything is bolted because the bolts that would go through would be holding the pack together and would be holding the bus bars together. The idea is once the pack is actually bonded, like before it's bonded, it's not really unsafe because you can touch all the cells together that you want. And then after it's bonded, you never take those bolts out anyway. So I think the idea is to assemble it and then never fuck with it. But it's still something still seems goofy to me, but like maybe I'm just naive. Yeah, good question. I guess you could, depending on the configuration of your pack, you could potentially have a pack where maybe there is a bus bar that goes across like, I don't know, 8 cells that's like 4 and 4. And maybe if all 4 of these cells are connected together and then you put a bolt through the middle, that's fine. Because then even if it touch all 4 of the cells, because yeah. Yep. So ta-da, there you go. That's one option. So that's square packing. Like I said, it's generally less space efficient. So if you want to get the maximum number of cells into a space, this is not the way to do it. But like I said, it can have other benefits. If you move to hex packing, that's the one that we did this year, and that generally has higher energy density. That's the one you see over here on the right. That's that classic like honeycomb hexagonal packing. The big thing I want to call out about hex packing is while it is the highest density, it means that the gaps between the cells is also super small, and the air doesn't have a straight path through the cells. Maybe that's a good thing. Maybe the fact that it's forcing air around the cells is advantageous, or maybe not. I don't know. What's up? That's a long ass time ago. I don't know yet. I don't know. But yeah, and so that would be another important thing is that like if you're deliberating between migrating to one of these, then maybe airflow doesn't matter if you're doing liquid cooling. If you're doing air cooling, maybe it does matter. I do know that in most like Teslas that I've seen, they use hex packing for all their stuff. So I'm assuming that that's the go-to, but they also have enough engineering resources that they can figure out how to fit cool stuff in weird small spaces. So. Yeah, they do liquid cooling with ribbons, is what to my knowledge. Like obviously that's not like insider information. That's just like if you Google Tesla battery pack teardown, you can find that people pull the cooling ribbons out of them.
Yeah, I was thinking this might be older too, like I might not be a Tesla, but like they have big full fledged on that.
Yep. Yes, that's another common approach that you'll see in stuff like plug-in hybrids. Because then rather than having to do all these ribbon things, then if you're let's say Chevy and you want to make a plug-in hybrid crossover thing, then you can just say, cool, let's just buy a cold plate, slap it onto the bottom with some thermally insulating adhesive, and then boom, now you have a brick that is cooled and it's done. I don't know. Something. Aluminum, maybe? I have genuinely no idea how they're manufactured. Well, but then the wrap on the cell is insulating.
Yeah, but okay, why do we shock ourselves?
So we shock ourselves because the fact that insulating wrap on the outside isn't connected to the cell in any way. Like if you grab the terminals, you spin it, it'll just rotate. And so the problem is that we use adhesive to keep our battery cells in place as we bond them. And so, well, I don't know because I've seen pictures of unshucked cells that are bonded. So maybe we're just stupid and it's fine. But also from our just very preliminary testing, we tried rotating. We're like, it can clearly spin in here without a problem. And well, and so that was our concern is we were like, this will probably mess with the bond, so let's not. But maybe we're stupid. Maybe it is actually fine.
Really tight and squeezing it.
I don't know. Well, and also one thing I will mention. What's up? I don't know.
But like, this is like,
I don't know.
We should get a bunch of battery bolts and pull everything.
Well, I thought about that. It's hard to get the bonding requirement, but yeah.
It sounds like the bolts are just practical. Like if there are bolts in every battery,
Yep.
that'd be fine.
But yeah, the other thing that I want to mention obviously is while hex packing is great and it has this high density and obviously comes the downside that you have very little spacing in between. Also, the annoying part is your batteries, most humans, when they start with CAD, they think in squares. Squares are really natural of a thing for us to think about. If you look around you, everything is squares and rectangles that are extruded. But the big part that I want to emphasize is our car is not a square and actively really doesn't like being square. Particularly because if you think about it, the area under the firewall is like a big trapezoid. The area you have available for the battery is a big trapezoid. And the great part is that hex packing really loves trapezoids because it really loves 60-degree angles on the side. And so that is an option, is potentially hex packing may actually be really helpful because rather than trying to make a square pack like we did this year, we made squares and rectangles and then trying to fit hexes into that, maybe just accept it and make them hexagonal. I don't know. What's up? Yeah, and so that's one of the parts is that like, oh, maybe it would be best to actually have the pack have two 60-degree sloped sides or maybe one 60-degree sloped side to actually fit it under the firewall better.
We could still also use like it follows like the same line, but it's not like it's supposed to pack together.
What's up? No. There is a number, I don't know this off the top of my head. I think it's something like 45, but you'd have to check because there's like rules limits on what the firewall angle is, so I don't remember off the top of my head.
Is the firewall like only like angled like that, or is it,
you can change the angle of it?
The seat and
yeah,
the car?
There's like some functional requirements about the shape, angle, and position of
Like,
the
is
firewall.
It, like, under the seat running up along the back, or
it's like a solid plate.
Gotcha.
Yeah. But yeah, it's also like aluminum. So
like, can you make it like two plates that are like welded together, or just like one solid piece?
You can make them separate plates as long as the idea of the firewall is that it separates all tractive system stuff. So that includes, batteries, motors, cooling, all of that from the driver. And that's why I've never been sure how we exactly got away with running our radiators off to the side of the car, because the fact that like you totally have line of sight to the driver from the radiator. I don't know how that's fine. So maybe that will be a problem this year, maybe not. I don't know. So.
That does sound like when I was looking last year, that is pretty normal to have like the radiator on the side.
Yeah, like a lot of teams hang their radiators off the side, and I'm not sure how that works or why that works. Because the rule very clearly says you have to have a firewall separating everything, including liquid cooling components, from the driver compartment. But like we just totally don't. And a lot of teams run radiators on one or both sides of their car in like a side pod. So I'm not sure. Don't know. Good luck.
The car, maybe there was one.
So I don't really know how that works.
yeah,
Yeah, it's just near the car. But yeah. The other thing that I want to mention about hex packing is if you think about it, if you do end up making something that is rectangle shaped, when you think about it, hex packing fundamentally has one side that likes being put into a rectangle and one side that does not like being put into a rectangle. So for example, let's say you had to take this design and continue it 5 more times, and that was one of your segments, like a lightsaber type thing. If you take this and you stretch it, that's basically if you stretch it to the right, that can be highly efficient because you have cells that are constantly pressed up against both of the long edges. And only are you wasting this space on the left and right end. So this empty air gap, it's only being wasted there. However, imagine I take this design and tile it upwards vertically. you now realize that these wasted spaces are going to be wasted on the entire side of the longer edge. And so that was one of the unfortunate oversights that we realized, like after we designed the segments and manufactured them, is we realized, oh wait, we just like did it the wrong direction for some reason. Yeah, and like that's unfortunate, tough. It's really appealing to stretch it upwards because then all of your cells that are in parallel are directly next to each other. Whereas if you stretch it to the right, then your cells like wiggle back and forth. And so it means your bus bars are more complicated of a shape. They're not just like a rectangle, but obviously, Dennis, as you've seen, you can pretty easily just design a bus bar that's whatever shape, and you can get it laser cut, and it's totally fine. Yeah, they look cool. They're totally fine. And so that's definitely a recommendation I'm gonna make, is that if we can move to more squiggly bus bars and moving to stretching, even if nothing else, literally just like rotating the cell orientation in the segments.
Like a really long bus bar is like.
Yeah, and so that's definitely a thing to consider when we're doing the actual packing within the segment. Yes. Okay, cool. So when it comes, so yeah, when it comes to your segments, the big thing is like, what shape do you want to make them? Obviously, what we did this year is we had the 6 8x10s where they're 8 cells wide, because it goes 4 down 10 and then 4 back up, so it's 8 wide and 10 tall. So they're pretty much rectangles. It seems like a better design from our understanding may be longer ones like the 4x20, where you take that, you maybe wiggle its shape a little bit, and then you can get high efficiency. You can really squeeze it in there. So the main things though that make it, that like really affect this shape and this overall configuration, is all the other stuff that goes in there too. Like, let's say you decide to make it like, I don't know, a 6x14 or whatever, and then the voltage sort of wraps around the pack, top, bottom. Then that now suddenly means your bus bar design gets more and more complicated, because now you have current that's flowing in a weird direction. Current isn't flowing across the thick part of the bus bar, it's flowing through the thin part of the bus bar. That's not great. And so there's a lot of these weird complexities that sort of pop out. Same thing, okay, now where do you put your, like, especially let's say, like for us, it was really easy. We could just slap the maintenance plugs on the top with the BMS and call it a day. But let's say you move to a, like having like a, like, you know, a parallelogram shaped segment. Now where do the bus bars go? Sorry, where do the maintenance plugs go? Where does the BMS go? If the BMS goes on the top and the top is the long side, you're again wasting a lot of space. And where do the maintenance plugs go? Maybe the maintenance plugs get sunken into the pack, or maybe they stick out of the top of the pack, but once again, that's wasting more space. And so there's a lot of questions that pop out of this. And so figuring out what shape you want, what rough shape to inform mechanical design, is like a really big thing to start initially. And I'd recommend spend as long as possible on that and get as many elements into consideration for that, because that will be like the thing that makes or breaks whether your pack is actually a lot better or not, is just figuring out that configuration. And I'd actively recommend, our configuration is bad, do not copy it. It is actively not a good choice. Well, it's because we were learning. I would not recommend copying our configuration. There is a limitation of kilowatt hours per segment, like the energy stored in each segment. There isn't a limit on the power output per segment.
Okay, are we at that segment?
We're close. The main thing that's annoying is that, according to the rule, like, so the actual energy density of a segment you calculate by taking the amp hours of the cell and multiplying it by the nominal voltage of that cell. That's how you actually calculate the energy. And for us, that means we're at like 5 megajoules per segment, and the rules limit is 6. The annoying part is that the rule says that because every pack is going to have a different discharge curve for the cells, they say you have to do the amp hour rating of the cell times the maximum voltage of those cells. And so when you use that calculation, which is non-standard and not representative of the energy you store, then you get like 5.8 megajoules per segment. And for that one, we're pretty close. And so that's always the important thing to differentiate, is thinking about what's your actual energy capacity and what's the weird rule calculation you have to do.
Does that weird rule apply to
So the number is calculating specifically the verbiage says the amp hour capacity of the cell times the maximum voltage of the cell. So if you say this cell will never go above 4 volts because of our management system, then now that's your calculation.
Okay.
Yeah. That's what CMU does.
I thought you can get the extra capacity. And I thought that for capacity, the mission company will run it when they say maximum, they mean like the maximum rating.
That CMU said that they submitted rules clarifications, and the judges said as long as the cell will never exceed, they want to calculate as whatever is the maximum voltage of that cell. So if you don't have it go above 4, let's say, then like that's fine. My understanding is that we would have to submit our own rules clarification for that to confirm that that is fine before moving forward with that. But that is what their guy said, and that sounds reasonable to me. So because then the idea is that then if you go above that, then already you're gonna see a voltage that exceeds the number that you cited, and then the energy meter will be like, what the fuck? Because the energy meter is checking your max voltage anyway. So, but yeah, yeah, obviously in terms of like the actual segment shape, we already talked a lot about, okay, cool, you can make them long, you can make them tall, you can make them thick, whatever. The big thing is also, the big part I want to emphasize is you can, like, irregular shapes, especially for hex packing, are great. I love that both of you are standing up. Why are you both standing? Do you need to piss? Oh. Okay, sure, cool. Yeah, so that's the big thing is that specifically if you do hex packing, maybe it turns out you still run air cooling because we can't figure out liquid cooling, or maybe the liquid cooling just uses a ribbon. Then and you still want to do hex packing, then yeah, I'd actively recommend use that shape. Don't keep thinking as boxes because our car is not boxes. Our car loves trapezoids and triangles and parallelograms. Like use that shape and make segments that are that shape. Really lean into it because like the whole reason our pack is so bad at fitting into the car is because we waste all the space on the firewall because we made big tall rectangles, and it would have been way better if we could have made really low flat parallelograms and shoved it into the firewall. That's only something that we've learned in the process of doing that. So obviously, like as you can think with a hexagon, it's all of your angles are at 60 degrees. So if you want to do a really quick rough out of a CAD, just slap in a parallelogram with 60-degree angles on the corners and then you're done. Cool. Yeah, the big part that I also want to emphasize is that it's really easy to get caught into the idea of, oh, we do 140S 4P configuration, so we need to have voltage that goes up in line. So you can only really do something that's 4 wide or 4 tall. And that's obviously not true. It's just a trade-off of how much more complicated do your bus bars get. So like, for example, if we're doing 4 in parallel, you could do a 6 tall pack that then rather than doing like, and so like, even though it may be a 4x20 configuration, it could actually be 6 by whatever that math comes out to be. And then yeah, your bus bars wiggle around the pack. You could also make it 5. You can make it 7. You can make it 9. That would get weird because obviously the odd numbers mean that you get weirder and weirder staggering and then more unique bus bar designs. With a 6, you can actually get away with one unique bus bar design. But now you have more current that's flowing in weird, non-normal direction, and BMS sensing gets more complicated. So.
Oh wait, I know.
I think it's totally fine for either side to do that. There's a lot of electrical considerations that go into designing it, but there's also a lot of mechanical considerations that go in, like the thermals of it, the packaging, how it's going to be located, how it's going to be mounted, as well as buying the material, manufacturing the part. So Dennis, I know, went through and designed a bus bar for us already this year, and that was fine. So I trust that electrical side could do that again, or mechanical side could do that. I think because you were also working pretty heavily with Louis to get assistance on how to figure out how to do the mounting and all that stuff for it. And a lot of that knowledge transfer about how heat dissipation works was stuff that I'm not transferred over. So I think both sides could handle it, but at a minimum, there should be some interaction about how that's working. And it's like with most things in the battery, it's like a chat about it. One person will do the majority of the work, but nothing is really done completely independently.
I did the heat house and everything else, like how are we locating targeting style, like if we looking at all paths and stuff like that. So if whoever is working on the segment or like the cell holder will be the computer getting a lot to figure out the spacing and shape as well.
Exactly.
Is there anything really stopping the bus bars from being like repeat designs? Like, what is the challenge for that?
The main thing is that the more complicated of a geometry your bus bar has, the harder it gets to approximate how much heat it's going to generate as current flows through it.
Oh,
And so, like, let's say, let me see if I can stop share for a second. Oh, hello. Let me see if I can pop this up and do a quick. If there's a marker in here, there is a marker. Cool. So one of the big things that you'll think about is, let's say I'm going to start drawing. So let's say you have 4 battery cells that are packed like this, and then you want to fill in the space in between them, like with bus bar. And so if you fill in all of this stuff with bus bar, then now it's basically fine to have all this be bus bar because all the current is really flowing from here to here, and then here to here, and here to here, and here to here. So you really don't have much bus bar, and it's very warm. And so that's your ideal situation. You have very wide, very short bus bars in the direction of current travel. Because as a reminder, you want the resistance of your bus bar to be essentially as low as possible. Oh, I guess I've got some weird shadowy stuff going on. Yeah, they can kind of see it. So you have some weird stuff going on. Because remember, oh gosh. Anyway, so remember the fact that your function for resistance, R, is your length equivalent resistance is equal to rho times the length over the area, where the idea is that this is like the resistivity of a material, so that's ohm meters. And then L, your length, is basically this length from where the current goes in, where the current goes out. And then A is your cross-sectional area. So that would be this width times the actual thickness of the material. And so what you want to do is obviously you want to make it as wide as possible and as thick as possible and reduce that length as much as possible, make the resistance super low. But now let's say, imagine that these 4 cells are connected together in parallel and these 4 are connected together in parallel. And you now need 180 amps to flow through this tiny brick in the middle. Now suddenly, to meet the same resistance number, that needs to be way thicker. Otherwise, it's going to generate a lot. And so that suddenly introduces the weirdness is now, let's say you do have you have the current actually squiggles around the battery pack in weird ways. Then you now need to make your bus bars thicker or more complex to accommodate that. There is a maximum recommended thickness. And then also, obviously, that adds to the thickness of your whole battery pack. So you can, Hess generally recommends a 1 to 2 millimeter thick bus bar. So that means you're talking in the range of a little bit under to a little bit over a 1/16 of an inch thickness. And while that's great, that also tells you that let's say you push it and you go all the way up to 3 millimeters of thickness and you make it copper to have really, really low resistance for like for your ohm meters number. Still you do end up running into limitations. Like you end up needing it to be pretty thick just to meet that. And then when you make it super thick, you have then bonds that go on top of that and bolt heads that may be going on top of that. And so now your whole pack might actually grow. If you say go from 1 millimeter to 3 millimeters, now your whole pack has grown by 6 millimeters on either side. And if you stack 6 segments, that's an inch. That your pack now just grew an inch because of the fact that you want to do a weird bus bar. And what we did this past year is we didn't really worry about it too much. We just made these changes. We made these compromises, said, oh, it's fine, it's fine, it's fine, it's fine. And then we realized that all the little changes that we made grew the pack by many inches just because we weren't actively being. So, it's one of those things where the individual change doesn't make a big difference. But doing that in many places causes a problem. So, yeah. Make sense? Oh, let's go back to screen sharing. Cool. Okay. Okay. So, but yeah, that's the big part that I want. Let me pop the screen back. That's the big part that I want to emphasize is that sounds awful. Is that while having something be the width of your parallel configuration makes things really easy to think about logically and easy to design bus bars. There's always that trade-off of, is it worth going through the extra 10 or 20 hours of pain designing and manufacturing the bus bars in exchange? Oh, that's where it stops, I guess. Is it worth going through the extra pain of the bus bars in exchange for making your pack easier to design or making your pack better? I don't know. As I know, we went through a lot. We have really easy bus bars, but we've now gone through a lot of pain that Louis and Ben have experienced because of the fact that how big the battery is. So, yep. Cool. Cool. All right, obviously this is just a little bit of stuff about rules. So obviously the segments are not supposed to exceed 6 megajoules. We already talked about that. That comes out to about 1.66 kilowatts of energy. Like I said, they do the weird calculation of the maximum cell voltage times the cell amp hour rating rather than like nominal. So you have to do that weird calc for the rules. Like I said, we're already pretty close to that number. And so that just means if you want to make the segment, if you want to go to lower number of segments, you might have to make some compromises. Let's say you do figure out, oh, you want to reduce the power output of the car and go to 3P, then you could probably go to 6 segments, no problem. But if you stay with our current configuration and go to 6 segments, I think you have to cut a series element out of every segment to make it fit in that energy capacity. What's it? Yes. And then obviously the segments aren't supposed to exceed 120 volts. I don't know why. I'm assuming that's like a safety rule. But yeah, for rules that you can't exceed 120 volts per thing, we're nowhere close to that. I think our maximum right now is like 84 volts. And obviously we're reaching like the energy limits. But I'm assuming this is in place because there's probably 1 or 2 teams that did like 1 cell in parallel and like 50 in series in a segment, and then we're like, wait, what the fuck? And I'm assuming this to try to deter having really high voltage segments that are then connected in parallel. Because, imagine you could make a 600 volt segment that you could then stack in multiple in parallel depending on how much power output you need in terms of energy. Maybe that's like a valid design. Maybe this is why they're trying to get rid of that. I don't know. But yeah, definitely not allowed to exceed the 120 volts. For us, that means you would need about 28 to 30 cells in series for any lithium ion battery. Obviously, we're nowhere near that. We're at 20, but you could potentially go up. I think the highest, like for us, once you go above like 23 per segment in series, is where you start to hit these limits. And like I said, after that, you'd have to decrease your serial count. Sorry, your parallel count. Yeah, someone asked, why do we have many segments? Because obviously there's a bit additional stuff that comes with each segment. So why don't we just do 1 segment or 2 segments, whatever? It's mostly this 6 megajoule limitation. Obviously the voltage also exists, but it's mostly moving down to 6 segments still gets tough. You have to start making compromises at 6, and then 5 and below to have the energy capacity we have, just doing the math out. If you have an 8.7 kilowatt hour battery and you divide it by 5, that's just not possible to get that energy capacity into that small number of segments. So, yeah. What? What do you mean the next slide? Is this slide 69? Nice. But yeah, so, yeah. So the big thing that so the big thing that I also mentioned earlier that I want to re-echo here is if you wanted to, we made all of our segments have the same configuration to make all of them all of them to be 20 in series, 4 in parallel. There's no rule saying that you can't make them different configurations. It's actually a thing in ESF that says like list the configuration of each individual segment in the order that they're in your pack, and then it like totals it all for you. So you could totally do a segment that has like 4 cells in it, and then right, because like you can imagine some cursed design where you have segments that are 1 individual cell, and there's no rule saying that we couldn't have like whatever it would be like 1,000 maintenance plugs in our pack. Yeah. I'm like, well, but that's the thing, like, so like. Exactly. I don't know. But yeah. And so that's the thing, is that maybe also a big thing I want to emphasize is that it's like the rules are obviously like a set of Oh, okay, it's pretty high. The rules obviously are a set of guidelines. One of the things that we spoke about with our ESF advisor just recently is that there are some rules that they just completely let us ignore because of the fact that the sentiment of the rule, like our updated designs, even though they don't follow the word of the rule, they follow the sentiment of the rule. Like this happened where they say that the big switch that you can use to turn on and off your high voltage system, the TSMS, the tractive system master switch, they want that to be the last switch before your contactors, before your AIRs. And so it's like, oh, okay, cool, we have to do this last. But then we were like, wait a second, our BMS is inside the battery. Why the fuck would we run a wire into the BMS and then have it go back out to the switch and then go back into the battery? That's stupid. And then we asked them, can we just like have the BMS be after that? And they're like, oh yeah, that's fine. The point of the rule is to just make sure that there isn't a lot of stuff after that switch because we want to reduce the length of the wiring.
The idea is they want the rest of the wire.
Mm-hmm. Exactly. Yeah. So sorry. There is an ESF reviewer. So we have a form called the Electrical Systems Form. Just like on the mechanical side, they have SES or the Structural Equivalency Sheet. Just like they have to submit SES that shows that our frame and our accumulator mounts are safe. Same thing, we have to do ESF, which is our electrical system form that shows all of our electrical system designs and shows that they are safe and rules compliant. And the idea is that when someone shows up to competition, they know that at a bare minimum, like the complicated stuff has all been checked beforehand in CAD with math, and not just like the judge looks at it and goes, yeah, this looks like the number, the drawings and the rules. Yeah, and so it's to make sure that someone actually reviewed it. Yep. And so the thing is that if you have, once you submit your ESF, to make sure that you have consistent feedback, you are only allowed to submit electrical rules clarifications to your ESF advisor. And so that's why you saw there was a period of time where we had like 3 or 4 rules clarifications that we sent out that all got, the response was talk to your ESF advisor. And I responded very passive aggressively being like, why? And then they explained like, yeah, it's to make sure that the feedback is consistent and is consistent and aware of what your specific design is. I was like, oh, okay, cool, that makes sense. So anyway, that's the thing. The long TLDR of this though is that you can feel free to do whatever unique design configurations you want. The only downside is that if you have one segment that's 10 in series and then one segment that's 25 in series, you now need to have different BMS designs or a BMS design that can accommodate that in some way. Yes.
So like start discharging that faster and then you basically end up with the lowest capacity.
So yeah, definitely always maintain parallel. Or if you wanted to not maintain parallel, you could do like, this would be so stupid, don't do this. But you could, for some reason, have 2 segments that are like 20S, 2P, and then run those 2 segments in parallel. I see 0 reason why you would ever do that. But like, you could.
You have 2 series segments, 20S, 2P, and parallel that with 2 segments that are 40S.
You could do that. Well, I mean, you'd hit the voltage limit, but like, still, like, yeah, but like that's the thing is that like the rules doesn't stop you from doing that. Like, don't, but like you could. And so that's the thing is you may find a particularly beneficial configuration that says, oh, this number doesn't divide evenly. So maybe it's just like we did the 6+1 configuration of having 6 of the same and 1 long boy. Maybe you find it's advantageous to not only have a long boy, have a differently shaped guy than for one of them that also has a different number of cells.
If you want to, you have to make sure they're completely perfectly balanced before you plug them in, or you get insanely high current with one. So not recommended.
Yep. And that's even, there's actually an option on the ESF that says, do you do series then parallel or parallel then series? And we picked the wrong option because I was stupid and misunderstood what it was saying. And literally like the ESF judge was like, are you sure? This is really stupid. No one ever does this. It's just an option because you can. But they were like, the whole point of that, yeah, you can that your segments, if you unplug them and do something and plug them back in, they can have massive shorts, and the cell voltages will unbalance from each other. So now you need to be tracking twice as many voltages. It was like, this is very unorthodox, and almost no one ever runs this configuration. But you can, you just don't.
Also, with the EMS line, I believe that is absolutely
Mhm.
but it should be not super difficult to modify it for it. So
Yeah. Okay, cool. So this stuff. Yeah, some reminders of pain points that we have had is maintenance plugs, having them actually be fully embedded in a segment. That was one thing that I talked about earlier in this slide deck about, how we have the maintenance plug stick out from the segment, which seems really cool because then your segment looks really dense, but then you realize you have this big old air gap for the cabling that just hovers above your segment that you need to put these big ass bars in there to be able to actually apply load paths vertically. Instead, probably a way better idea to just like have the maintenance plugs be stuck into part of the square of the segment. Do you guys remember what I mean when I say that? Dennis, you look like you don't. How?
The line right before, you said like the plug into the square of the segment.
Oh, like the maintenance plugs should be sunken into probably, it seems to me like sinking the maintenance plug into the segment is like a good idea. So that way you can, yeah, because then you need the support bars that have to come down, and then you're wasting airspace. So ideally, you would just have like an area that's intended for the maintenance plugs and cable managing stuff.
if you want to go down. Or it's just extremely standard, relatively inexpensive connector. The XT90 can handle 90 amps at 500 volts apparently.
Maintenance plug.
And yeah, we could like replace the maintenance plugs with this just like standard.
Needs to have positive locking, but I'm sure you could find something similar with a positively locking mechanism. But like I said, I'm sure that there is something similar that exists that has that feature available.
Or you
So
could build a little.
this is true.
Walking, like we engage it, and it doesn't come with, right?
The idea is that the idea of positive locking is that you have to actively do something to be able to unplug it, and vibration alone cannot unplug the thing.
What is this also? But for the maintenance plug, is that like that's just in terms of mounting it?
Well, and so for us, that means that number one, any bolted connection in the high current path has to have positive locking. So for us, we use lock nuts. It's pretty easy. You just have a bolt that goes through with a lock nut on it. And the nylock makes sure that you're actually deforming nylon to like make sure that vibration can't rattle it off. And for the actual maintenance plug to plug connection itself, they're not just friction mounts. They also have like a little button that you press that like holds it on.
Okay, so like the plug, like,
yep, every connection. But yeah, I know it's very common also to have like a clip or a button or like a little clasp or something that slides on. Yep. Well, everything in the high current path has to have that. Yeah. Maybe someone can try to establish relations with Royal in the future, but I don't know. Anyway, yeah. So, obviously talked about sinking the maintenance plugs into the segment. That's an awesome idea. That obviously comes at the cost of if you want to optimize segment density, your segment density is going to go down now because you're moving the maintenance plug into the segment. But it should increase the overall pack density. Same thing. The shape is now going to have to get weirder because of the fact that since you're sinking it in, you now can't have like a nice little rectangle. You now have like a rectangle that has plugs going into it, and so you're going to need to make some squiggly L shape or something like that. But if you're already abusing weird shapes, then weird shapes are weird shapes, and you can make weirder shapes. So, yay. Yeah, BMS wiring, obviously just like there was so much pain this year of figuring out how to do the wiring because we had to do the custom boards and then we have to epoxy the boards. And Hello? Yes, so no, like the top side. I guess. I know what I meant by this. Is in our in the 8x10s, you have to like send a PCB that goes over top of one bus bar to the next bar to the next bar to the next bar to be able to access the lower voltages. And so if we were to do wiring, you would have higher voltages running across on top of each other. With the 4x20, the bus bars all just pop up at the end. And so you can just put a board that goes across it and nothing ever overlaps onto lower ones, I think is what I was getting at there. So that might make it, because especially if you wanted to do something like actual wiring, that might make the wiring easier.
Where,
Mhm.
like, where all of the concerns with 1.4
No, I just mean in terms of like designing the actual sensing board. It will like, if you could have little tabs that stuck up on the side straight to the BMS, then imagine if we didn't need the sense boards at all, if we didn't need wiring at all, we could just have the ends of the bus bars just like stick up. And then, and so I should see. Okay. Hello, everybody. Welcome back.
Would you ever advise going back to wiring rather than just using the PCBs? You just use the PCB.
I think we are still far away from an optimal solution there. I don't know what the optimal solution looks like. I think moving to a PCB that plugs directly into another PCB would be like the most optimal. But there are definitely some downsides that come with that in terms of testability, and then your manufacturing tolerance. Super tight.
What a lot of like serious battery packs do, like if you take apart the Dyson vacuum cleaner battery, they're with nickel strips, but you could probably do something related. They have these spot welded nickel strips, which are basically the equivalent of the bus bar, are bent into a shape where they actually go directly to the BMS board, and then you don't need another board to connect to because all the voltages just go directly to that board.
Yep. I've also seen some cool stuff where I saw all of the bus bars. Yeah, the bus bar actually just has a little nub that sticks out the side, and then the BMS board just sits straight on top of it, and then there's like a bolt. Yeah, and so then and
why do we have the BMS?
well, for us, because of the fact that we designed the 8x20s the 8x10s first, and then figured out, and then just like put the BMS on top of it. And so for us, there was no way for us to have all of those stick out. But yeah, if you did like, if we had started and everything had been a 4x20 from the beginning, then yeah, we potentially may have designed a BMS where all of the bus bars just stick straight up at the top. And then the BMS just, maybe you put little bends on the corner with a hole, and then maybe you just bolt it through. Done.
Oh.
But now your manufacturing tolerances are super tight.
That sounds nice.
And then the BMS also is a total pain in the ass to uninstall.
Yeah.
And just be better on the.
No, he's right about, because like,
But
it
it
sounds nice. Like, you can do it, it sounds so nice.
Wait, okay, so why does the BMS have this? We can't tell.
It could.
It can, but you need more wires to it.
Yeah.
Yeah, but like if the bus bars are already on the side, can't we just put like a BMS on?
Bus bars are on both sides.
Yeah.
The reason the BMS is where it is because with our maintenance plugs, we have room there, and it's like equidistant from both sides. We need to sense everything on both sides.
But you're right. There is no rule saying that the BMS, because like as long as the BMSs have some way to talk to each other and like actually know a relative voltage to each other, there's probably a way that you could have a BMS board on either side. But also that comes into the question of where do you want to be adding space and where can you afford to add space?
If you want to completely redesign the entire BMS from scratch, you could even have like a little board on each cell that monitors its voltage and temperature and sends that wirelessly to the main board.
That sounds like a.
But you could do it.
So you can do it.
Oh, and so that's the big
Or
question.
each cell group.
Yeah.
Each cell. That would be a fully distributed instead of a scientific setup.
How would you like fit that bit. Yes.
If it's small, you can do anything.
Yeah, but like, what exactly needs to be on the units?
Just voltage, temperature, that's it.
And balance.
And balancing. Yeah.
Oh, so it's not that hard to just kind of.
Well, not that hard in theory. You now have to make 140 of those.
Oh, yeah, no.
Yeah. Yeah,
But
but
also like,
Well, you won't have to make 140, it'd be pretty.
yeah, we
Yeah.
have 140 travel.
140 series.
We have 560,000.
Yeah.
Oh, I forgot.
Uh-huh. Anyway, what's up?
What's the reason that we did? I don't have like a rules.
Yes. So if you put one segment on top of another segment, you need to prove with FEA or something that all of the load, like the load path for all the forces supporting the upper segment doesn't go through the lower segment. And so I'm assuming, like, basically from what I've talked to other teams, it sounds like other teams also have said, fuck that and not bothered. Like, there's no rule saying, because the thing that we looked at is we realized, why would you ever make a segment sit on top of another one if you can just have one taller segment? And so the question that it always comes down to, like for us, we could have done segments that are long and skinny and sat two of them on top of each other, but then you have to prove that no force goes through it. And so instead you can just cut them in half and then make them tall and ta-da, you have the 8x10s. So but
So our accumulator right now is really tall.
Yep.
Is there a way to like move stuff around in the car to make it like flatter?
yeah, that all gets into the idea that I talked about of hex packing, changing the direction that the cells are oriented in, and more effectively using trapezoids instead of sorry, more effectively using like other shapes.
If we also 4x3s.
Then the packet's longer.
Yeah, so like, is there space in the car to make it longer and
When you do all the different configurations, there are a bunch that pop out that could work fine. Yeah. I think if you do R7 configuration, and then if you basically take R 4x20 with stretch it out a little bit to do something else, I think it ends up getting too long that it hits diff. So I think so. But also that was like, this was when I was going through like 5 or 10 different configurations. You may find that actually, oh, maybe if you make the standoffs and the bonds really low profile and the bus bars really low profile, and you maybe use to stretch stuff out a little bit, maybe you find, oh, actually, we can make this pack fit between the firewall and the diff. Or there's no rule saying that the diff has to be where it is. Like there are limitations. There are limits on the track width and track size of the car, but there are teams that stretch out their cars. So there's an option that we could say, oh, actually, maybe we want to stretch out our car or shrink our car. Because those are normally things that on the mechanical side, the team doesn't really see a lot of change on the mechanical side, which is really unfortunate. Like I know Baja this past year stretched their car by like an inch because it made the design of a whole bunch of stuff in the front of their car easier. And for us, that's totally something that we could and should have as an option on the table, is not just saying, oh, things are this size because they are this size, and then we can maybe wiggle the frame a little bit. Like, no, it should be on the table that like maybe we can actually change fundamentally the whole shape and size of the car to better accommodate the battery.
Wait, it felt like the accumulator did go underneath the driver, like how the gas did.
Yeah, actually, I think I have a picture somewhere.
Right now it does, right?
Yeah, well,
It's
it
stopped.
goes a little under the driver, but not significantly.
Yeah. Because I could like imagine super long and skinny pack that just goes the length of the driver.
Yeah, so I don't know why my laptop is being like stupidly slow right now. Yeah, so like here actually, if you look at, this is a picture of the frame, and I've drawn in roughly where we actually do have space to put the accumulator. So the shape for the accumulator is roughly this much space available to you. Fits in roughly there. Because obviously the diff goes in the rear, and then the motor goes up in this area. One option is that you could say, oh, maybe let's make the battery taller and then let's drop the motor down here. That's one option. That's what a lot of teams do. A lot of teams will run their motor lower or in here, or they'll have the motor really low down, and then they make their battery shorter, and then they'll make their battery stretch further this way and then go up a little more. And so they'll have battery cells that are down in this area. And then rather than putting their contactors and all that stuff at the back of the car, they put that on top. But now that means you have a lot more pain in terms of whenever you want to service or remove a segment, you now need to take out the whole fucking set of contactors and everything to get in there, which is a little more annoying. But hey, the rules don't tell you that the pack has to be easy to maintenance.
How does that work?
What do you mean? Oh, yeah, if you have the diff in here, a lot of teams also will do a combo diff motor mount.
Okay, that makes more sense.
Yeah.
I was going to say, I feel like there's just no space.
Yeah, no. And so that's a common thing that you'll actually, if you look up, if you like go online and you try to find like Formula SAE designs, you'll find that there are a number of teams that actually do that where they'll have like one big structure that just holds the motor and the diff in place. And there's just a little tensioning mechanism there.
How close are you? Like, do you still need the sprocket? I mean, how do you fit the difference in like gear ratios?
Mm-hmm. That's something that I've seen pictures, but I don't know how that would actually work.
But I feel like at that point the motor's too close because currently our motor is where it is because we wanted to make it like this sprocket slightly larger because the motor is too close and it's already like pretty far away.
Yeah.
The way you're describing it, I feel like
it's super tight.
To have a gear ratio.
Well, you could always do, rather than having a chain with a sprocket, you could just do gears. Because remember, the whole, because there's all those rules, I guess I don't even know if it's rules, but like functionally, like you can have them be a certain, like they have to have spacing between them with a chain around it. And so it's like, my understanding is that, yeah, if you want to squish stuff closer together, you could squish it closer together and actually have just gears that just directly mesh.
That's like allowed in rules, that seems very unsafe.
I don't know. But like, that the world is your oyster. What's up? Oh, yeah, don't worry about it. It's moving.
It's not moving.
Ask this guy.
It's staying where it is.
Is the diff moving? Oh, you're adding an extension. Hey, I saw this.
There's a couple different rationales. But we did a lot of brainstorming.
I saw.
Not what happened. You know what happened. It's pretty straightforward. We were going with the motor to the left, and it got talked about, and I think we assumed it happened. And it did not happen.
Oh.
Which is whatever, but it is what it is.
Oh.
It's also positive in a sense because the diff would not have been able to go in the motor with what it was supposed to. Like I designed the mount not knowing that the diff was right there. That was not something that I knew.
Yep. Oh, anyway, but yeah, so
which is very easy. There was already a spacer in there for the chain, and now you just add one.
Cool. But yeah, so obviously, going through a few more things. Obviously, we already talked about the BMS sensing stuff, the maintenance plug stuff, and then finally we also have cooling. Obviously, my cooling child here. Yeah, obviously we're really new to this and we need to do, like, once again, just like with the energy draw, we really don't have a good idea of how this works until we test it empirically and go out there on a track, no matter how much simulation stuff we do. And same thing with the cooling. We have now done some small scale empirical testing that gives us some idea. And that's better than nothing. But it's still, we need to really bring this out to the track and actually see, is this a problem? How does this actually perform? And that's definitely something that I want to heavily emphasize, especially on the mechanical side of things, that as you're going into battery pack design for next year, that it really needs to be both using the data that we collect from this year and then doing empirical testing to validate new changes. Because no matter how much data we collect this year, and if you run the best simulation in the world, our simulations are only as good as the data being used to set them up. And so if you now say, oh, actually, we had problems with air cooling, so we want to reduce our air resistance by moving to square packing, just go make a jig and test it. Don't like just only, yeah, if you only run a simulation, then you don't know if your simulation is necessarily set up accurately. And likewise, if you only run an empirical test, you don't know if your empirical test will scale up appropriately. And so you want to do that back and forth constantly of run a simulation on a small scale rig, run the empirical test on a small scale rig to validate a new design or a new approach, and then scale that up in the simulation to see how that performs, because you now know that your simulations are accurate. So but it's more effort, it's more time, and usually we're too lazy to do that. But the alternative option of what we've done this year of, yeah, let's just pick something and then hope it's fine, or only run a simulation is just really not acceptable. Like I know stuff like the aerodynamics team does a lot of that, where it's like, oh yeah, let's just run a simulation and say it's better in simulation. But fundamentally for like the air for the wings, where it doesn't really matter what the fuck happens, because the only feedback we have is the drivers say it feels a little bit better. That's just not an acceptable level, like a not acceptable criteria for the battery in the car, like the bomb. We have a little bit stricter criteria, but it's definitely not a thing that should be copied from this year.
Got a button that injects the battery out of the car.
The quick disconnect. Mm-hmm.
That's called the driver.
But then it's the obstacle for the other driver.
Oh, you just cruise, roll to the finish
What
line.
if we use like one cell at a time? Once the cells get drained, we just eject. them.
Oh.
These stations.
It doesn't have to like follow the lithium ion safety if it's not.
Well, yeah, because there's the cooling tubes, right? So we wrap the cooling tubes like it's like the chain of bullets in a Gatling gun, and then when a battery
Jesus
is charged, shoot it out.
Okay.
One battery, well, we have to one battery at a time, because each battery can only output like a peak of like 500 watts or so.
Wait, so I know like we use rechargeable because obviously,
Yes, we use rechargeable batteries.
but like,
Good in energy.
is there a way like any teams use non-rechargeable? Just let it
So-
work once.
So to give you an idea of lithium ion batteries versus non-rechargeable batteries, you know how you can buy like disposable electronic cigarettes
Yeah.
that you throw them away and they're not rechargeable?
When you use it once,
They still have a lithium ion battery in
Oh,
them,
okay.
because you just can't get that energy and power that's
Mm-hmm. Yeah.
let's just run on the those.
Mm-hmm. But yeah, and so that's something that was, so to give some background, that was the point of the air cooling project this year. Is my advice was go through and do testing on the empirical small scale pack, so that way we can get rough number, like do that in combination with sims to be able to get rough numbers for what the performance is going to be. And then the idea is, oh, they'll finish that in the first few months of the year, no problems, because they'll do the sims over the summer, some empirical testing in fall, no issues. And then they'll be able to spend the rest of the year prepping for next year's designs by doing alternative battery configurations and trying different ways that we can get more cooling through the pack. But instead, the year ended up kind of getting thrown away, not really produced any results. Sorry. And so basically what ended up happening is they instead ended up having poor guidance and then wasted like 8 months on doing simulations that yielded no results and then they refused to say that empirical was a good idea. And then we did empirical testing. We have values from that, but because it was done so late, now it's not really, it's like kind of useful, but it's not super useful because we just have the battery now. And it means that now no investigation has been done into any alternative configurations or designs. And so there is now no knowledge, and someone will have to try to figure out how to do that over the summer when the battery has to get designed. So that's already kind of fucked. And so it's going to be kind of fucked rolling over into next year. So that's what happens when you have a project that you let do nothing the whole year. Not unfortunate, but like that's the spot we're in. And that is. So yep. And the idea is that would just be something that's fixed and improved going into the future, is just making sure that project actually can really generate results by whatever means, whether that's through empirical testing or that's through simulations or whatever, get actual results out, and then cross-validate them in as many ways as possible, and then really set up ways to actually learn how to improve it.
So if all the like design work with the three, at least for the electrical side is
And a lot of the mechanical stuff.
then what happens during the
A lot of that is still manufacturing.
Oh, it takes that long.
Well, the answer is I do not have a good idea of the timeline for manufacturing the electrical elements of the battery, because of the fact that it was a learning experience this year and we spent a lot of time redesigning and fixing things. There's a 50% chance that both the electrical and mechanical sides will end up spending a lot of time throughout the year just on manufacturing and testing. And because obviously you'll have a working car that you can test more stuff with, you have a second motor.
We can also like just bomb stuff up. And
Yeah.
testing like
And then there's also the alternative option of potentially you go through and you find so potentially there's also the option of maybe it's like the frame project where they go through and the frame is fully designed and manufactured by end of fall. And then you look and realize, oh, actually, like it doesn't matter. They just move on and do other projects instead. So that's another option too, is that maybe the battery people also then, like, a battery could be an entirely summer, fall, winter manufacturing project. And then it gets done by the end of winter, and then all of spring is then really doing design docs, validation, testing, and then also moving over to help out with, doing design work to prep for the future year. I don't know.
Also, the transition is like, we're like, oh, it's kind of funky right now.
Yeah.
And
Yeah, exactly. What's up?
What design dogs do?
Competition.
yeah.
Mhm.
Very technical.
We haven't done, as far as I know, we haven't done any.
You should do this.
Or this segment.
Yep. And obviously, I've talked a lot about air cooling stuff and about battery cooling in general, but obviously liquid cooling, if you guys want to jump into liquid cooling, that's obviously a whole big can of worms because of the failure modes of it are obviously really bad, and you have to make decisions on if that's going to be the direction for cooling like pretty early on. So I think liquid cooling is awesome and I would strongly recommend it, but I would only recommend it if you have people who are willing to put in the work to make it happen and also have demonstrated a history of being able to act on, test, and deliver a product that actually works and tested to work. So like I know Yusuf is interested in doing that right now. I think he definitely, of the people on the team, would be a great person to try to do that. But I do think that's something that like that testing would have to be done now in person, because I fundamentally believe that if there is no empirical testing done of liquid cooling, that is not going to be a safe battery and not a battery I would recommend working
So
with.
how do you even deal with the failure mode? Because obviously if there's a leak, like what do we do?
Here's one, that's gonna have a water sensor.
Yeah, or
That's
maybe
like a thing.
because also the big thing about failure modes is like things don't necessarily spontaneously go wrong. There is a cause for something going wrong. Like for example, let's say you did want to run one of these ribbons through your battery pack. That ribbon isn't just going to explode. Like it's not going to just cut itself. It has to get cut on something. And so maybe the FMEA is, oh, there's a cut in the ribbon and it starts leaking water. And so then maybe the resolution for that is, number one, make sure that there are no sharp edges that ever go near that. So maybe the pack is intentionally designed in such a way where that is enclosed and it's all smooth surfaces around it. And maybe number two, like Joshua mentioned, yeah, you can put in like a liquid sensor or a humidity sensor or something in the pack to detect if there is a failure, or maybe like a water pressure sensor that can detect that drop in pressure and say, oh, something is wrong, turn off the pack. Or maybe you run mineral oil through. I don't know if that would work because it's a completely different viscosity, but it's like mineral oil is non-conductive and doesn't generally get ionized. And so maybe you could do that.
Yeah, what if you just don't use ribbons at all? Just run mineral oil.
Weight. It's mostly weight.
There's the entire accumulator and mineral oil.
I thought about
That's the thing. I saw
That's
that.
just so much of
What if
it.
you get 5 gallons of mineral oil?
Isn't there?
Dump that
something-
bad boy.
That's about 5 goes.
5 gallons is 5-gallon jugs.
All I'm saying is it would be super cool.
Yep.
I saw like a thing where like a company that makes servers has their entire like they each have the server submerged in.
Yeah.
3M
That should be
Maybe
super flammable.
No.
design.
Nah, mineral oil isn't that fun.
Yeah, that sounds baller.
Most oils are, but mineral oil, to my knowledge,
I feel like
Let's put pouch cells in a giant pouch filled with mineral oil.
Mm-hmm.
No, use the.
Yeah.
3M makes their special stuff for it.
Anyway, it seems like we're getting off track a little bit. So what I'll probably say is, if people are cool with it, I'll say this is probably the end for today. We have at least another presentation worth of content. Essentially the stuff that I have remaining, just because we're already at what? We're at 71, so there's 10 slides remaining. I think like 6 of them are basically just talking about the benefits of pointing cells in the different directions. So it's like, basically, do you want your cells to be up, down, left, right, or forward, back? And it's like,
yeah,
I'll back this.
right.
so our current pack, they are front pack.
Oh, I'm thinking, sorry.
Yeah, the actual direction of the cells.
Okay,
And
I was thinking.
yeah,
Yeah, exactly. Look at this.
But yeah, and so you see like 5 of my remaining 10 slides are basically just talking about the different stuff. Actually, how about I'll finish talking about that and then we'll talk more about configuration next time. Yeah, the TLDR is that there's really 4 different options. You have up down, which is the way that they do it in real electric cars. The advantage is that air or coolant, whatever, can flow left, right through the pack. Or by the way, when I say everything from the perspective of the driver. So front back would be front and front of the driver, rear of the driver, left, right is driver, left, driver, right. Up down is up. So obviously the cells up down, this is how they do it in real cars. The main problem though is that it's hard to scale it in our car because we like, in a Tesla, you can put a really big skateboard on the bottom that's really big and wide and flat. In our car, we don't have as much space. I don't know if we can shove it all the way under the driver. So we really just have the area behind the firewall. And so there's a few more limitations there about where you can really put the pack and how you can package it. For us, I don't know if it's actually possible to get all the cells we want in a vertical configuration without stacking segments. But it is quite nice because it means your CG is automatically very low. And it means that cooling is generally pretty easy. Oh, one thing that's also worth mentioning here is this leans pretty heavily towards rim bonding, where you put a cold plate or something on the bottom of the pack, rim bond everything on the top, and all the BMS stuff would sit on the top. And that's how, real companies do it. That seems cool, it seems really easy, but there's obviously a complexity that comes with that. Your bus bars get more complicated, rim bonding is more complicated, and your actual segments are a lot more integrated.
But in terms of like the
He raised his hand first.
complexity, is that
No, not you, Joshua. That's fine.
We can get an 80 kilowatt hydrogen fuel cell stack for the low price of between $100,000 and $200,000.
Oh, what a man of the economy.
You want to donate your full salary for the next couple of years?
Anyway, thank you. What were you saying?
In terms of like rim bonding complexity, is that just is that on past like it's they're dealing with like the complexity of like putting it on the rim or
Well, there's a lot of complexity and safety considerations that now come with that yeah, we cannot fuck up because if our bus bars wiggle or anything, then they don't really have the option to rebond it because there isn't space.
And we can't spot weld.
And we have to give them a lot more information and resources because they now need to have a highly accurate CAD of exactly what our battery pack looks like. Because, if you look at our current battery pack, it's pretty clear that it's kind of eyeballed. We would have to give them a very specific, we might even have to work with them and say like, okay, cool, might have to do the machine instructions or something like that for them to give them exactly like to the millimeter where it has to bond it. Because obviously your bonding area is super small. Also, the design of the lip on your cell holder now gets weirder. And the design of your bus bars is now totally different. But now your bus bars now are only on one side, so you have half the material and space available to you. They have to get thicker. And it's now you have both sides of your batteries exposed. And so if you drop anything into anywhere on your pack, you die. So you can, and then also the question becomes, how the fuck do you measure the temperature? The temperature has to be measured on the negative terminal by rules. And so how do you measure the temperature of that? I don't know.
You just stick a little temperature probe down the bottom.
Yeah, but it has to be like, well, remember the negative
the negative terminal
is the entire casing. But the thing is that how do you get it in there physically? You have to do like a thermal adhesive. You can't just stick it there.
Can't you just thermal adhesive on like this?
Does that mean you now thermal adhesive that before you assemble the pack? It's a lot of foreplay. You could do that. And how do you get the wires out of there? And so the thing is, maybe that's the solution, but it's just there's just more planning that has to go into it, and then that's more stuff that has to be finalized.
The BMS can just top, and then the sensor is just
What's up? Oh, I've been doing everything. Basically everything for the battery that doesn't get done, I've been just doing. Someone's gonna have to do it next year because it's not me. So yeah, no, that's I don't care for this year. It's more for next year. Yeah, so that'll be someone's domain. Probably powertrain or energetics. But anyway, so yeah, that's a whole thing that I recommend and encourage you cautiously consider all of these different fun options. They're super cool and super exciting. But obviously they come with a lot of complexity. Like maybe it turns out you can do like a Tesla style battery pack where it's super flat and sits at the bottom of the car and perfectly fills the shape. And maybe you have a weird shape and you have 20 segments, and then you have maintenance plugs that auto click into each other. I don't know. Cool. Yeah, obviously left right is something where it's kind of sucks because the fact that you can't really cool vertically, you kind of have to cool like across the pack. And so that means this you can only really cool from the front to the back, which adds a bunch of annoyance because the fact that if you're cooling front to back, you can't have holes on the front of the accumulator. So you would kind of have to either have holes on the bottom, which is gross.
All the weight would also go on top of ribbons.
No, you'd still have a cell holder around it. That's fine. But yeah, this basically this is cool and all because like left right, it means that yeah, now your air cooling has to, if you do air cooling, then now the air has to flow. You would have to have like a channel where the air could like flow in from the side or the bottom and then like wrap around the pack to go through it. So that gets kind of weird. You get into like negative pressure designs. It might turn out that that is best from a packing perspective. And actually the design I was going to show does that from a packing perspective is the best. But it definitely fucks air cooling pretty hard. If you have like ribbon cooling, then that might not be a problem because you can just have a ribbon wiggle through it and then have radiators at the back. But you would then have to commit to the liquid cooling. Or now if you have cold plates, then you have cold plates between each segment, which means suddenly your width expands rapidly. So generally this seems to have the least advantages if you want to do air cooling. So I think this one is really reliant on either saying air cooling is just going to get fucked by it or doing liquid cooling. And then finally, the front to back configuration. It's the one that we use this year. It's to me the most logical, where you can stack them upwards pretty flexibly, and you can just push air across the pack. This seems to be a pretty common configuration. The only thing that's kind of annoying is that obviously it means that you're like it's fine. It's kind of mid. It doesn't really have any nice advantages. There's no super easy way to cool it because now if you have ribbons, then the ribbons have to go out the side of the pack, which means you still need to put radiators on the side. So it's about the same as air cooling. It does mean that it's nice though you have flexibility up down. It just means your front to back flexibility is terrible. And this one really sucks at getting the shape under the firewall. Because if you notice with the other one where you do left right, you can actually make a weird geometry that slides perfectly underneath the firewall. This one can't do that because this one has the fact that they're front back, and you generally don't want to have cylinders like staggered at weird angles from each other. This one, if you do anything with any amount of height, this is why we struggled to get far under the firewall. It's because even the 4x20, which is a pretty short segment, still struggles to get far in there.
Would this also be like harder to do? I mean, because I'm just thinking like liquid cooling, you have a cold plate that like you're either on the bottom, like the intakes at the bottom or at the top, that like pump would have to work harder to.
Yeah. Yep, probably. So yeah, this like I said, it's the one we used this year, and it seems the best from like an air cooling perspective, but from a packaging perspective, it has problems. So, and then, wow. The last thing that I want to mention is there's no rule saying that you can't pack cells in like some weird fucking direction. Like you could do them at like a 45-degree angle. I don't know why you would do that. I don't like literally. You see, my one comment is I see no advantage to non-cardinal directions.
Because like the engines, the pistons are like,
that's
Yeah, like
I
mean, hey, like I said, I have nothing against it. Like if you can, like I do think there's definitely this could be like a cool thing to like keep it in your back pocket of like, oh, if you're designing and you happen to come across like a weird problem, and you're like, let's throw shit at the wall and see what sticks. This could be a good thing to keep in the back pocket as an option, but I currently see no reason to do this. But like, don't hate. Like, maybe there's a design where the segments actually sit staggered on top of each other, and then the maintenance plug and the BMS board go in the triangle formed by stacking them as rectangles. I have no fucking idea.
we make trapezoidal segments, but like they fit together like a giant hexagon, and there's a giant hexagon hole through the middle that we
Sure. I have no fucking idea. So that's what I mean. Like that, maybe there's a configuration, but I don't see why. Cool. And then we'll chat more about we'll finish up our last stuff about segment configuration next time, because all we're really going to show off is some potential designs that I put together, the available space, and then really the big conversations that you're having and the big things that I've learned as I sort of walk around different options.
Yay.
Cool. We're finally finishing the slide deck. Like a month ago. Yes. Okay. Unless there's any other questions, I'm going to end the recording. Awesome. Thanks, everybody.
The water has to travel through. So